Hey everybody, Mr. Gustin here, back with another video for you all. This time it's for worksheet 7, asymmetric angled launches. We have an example problem and we have a data table for us to fill in again. What I would like you to do is make sure you're on worksheet 17 and we've read this problem. It looks like a soccer ball is kicked at a velocity of 15 meters per second. So I'm going to go ahead and sketch that right on my image. 15 meters per second. That's the initial velocity. At an angle of 30 degrees. That's theta, 30 degrees. We can even add that over here, angle of 30 degrees. And it is kicked at a height that is 10 meters above the ground. It's pretty high above the ground. Weird. All right, let's list all variables. We can determine their values out in kinematic equations. Let's just break this thing down as we would normally. First things first, acceleration in the x direction. There's no horizontal gravity, so 0. How about acceleration in the y direction? Oh, there definitely is vertical gravity here. Gravity always exists in that direction. Negative 9.8. All right. And I'm looking at my image here. It's a little different this time. I'm going A, B, C, and then D is a little different. D is like below the original point of A. But if I go ahead and take a peek at this, and I kind of sketch this straight across, A and C are going to be at the same height. So the symmetry things we've been looking at in the past, A and C are going to be the symmetric areas. B is going to be the top or the apex. So kind of my physics at the top is still going to be the same up there. So my velocity in the y direction at point B, well, I know that's 0 because it's my apex. Okay, I've already started filling quite a few things in. Let's go ahead and analyze what's going on here initially. Well, here's my vector triangle. There's Vx. Here is Vy. If you don't remember, Vy is going to be equal to V initial times, because it's the opposite side, times the sine of the original angle. Vx will be equal to the initial velocity, and this is the same side, or the adjacent side of the triangle, times the cosine of theta. I'm going to end up with this being 15 times the cosine of 30 degrees. And this will be 15 times the sine of 30 degrees. Go ahead and calculate those. I'll do the same. All right, for my initial y velocity, I get 7.5 meters per second. And for my x velocity, I get 1.3 meters per second. And in the y direction, 7.5. A quick check you can make is that my Vx and my Vy must always be smaller than my velocity vector in total. All right, thinking back, velocity in the x direction, there's no acceleration. Guess what? That means it is a constant velocity in the x direction the entire time, even at point D. Done. All right, my velocity at B, we know the velocity at B is only horizontal velocity, so I can read this straight across. My velocity at B is going to be 1.3 meters per second. I can use my symmetry rules between A and C and figure out, hey, if it was initially positive 7.5 meters per second upward. Well, now I know it's going to be downward at negative 7.5 meters per second. And the total velocity, right, the resultant vector velocity, excuse me, is going to be 15 meters per second downward at 30 degrees. This was upward at 30 degrees, downward 30 degrees. Holy smokes, folks. Symmetry has really helped me here. Let's analyze the last part of the launch, okay? The last part of the launch, I really need to figure out what this vertical velocity is. I know it's going to hit the ground at a different angle than it was originally at point C. I see that there's going to be this velocity vector right there and this horizontal velocity vector there. We know the horizontal velocity vector is going to stay the same, but how do I calculate this new vertical velocity vector? Well, it's a lot easier than you actually might think. Let's look at what I know about between point C and point D. Right? From C to D, here's what I know. I know that the velocity at C is equal to negative 7.5 meters per second. I know that the acceleration, I'm going to lower this a little bit so y'all can see me. I know that the acceleration from C to D is equal to G. Okay? I know that the change in Y is equal to 10 meters. It tells me that right here. Remember, the ball was kicked 10 meters above the ground, while from C to D, it's a difference of 10 meters. What am I looking for? What are my unknowns? The only unknown that I have is my velocity at point D. I wonder if there's an equation that relates velocities and position. Velocities and position. Well, there totally is. It's the squares equation. The velocity at D, which is my final velocity, squared, is equal to the velocity at C squared plus 2G delta Y. This equation here will help me find, it's a kinematics equation, to help me find the remaining section. This remaining section of this motion. Let's do it. VD squared equals negative 7.5 squared plus 2 times negative 9.8 times negative 10. Why am I using negative 10? Because it goes down 10 meters. If it were going up, I would use positive 10. Here we go. Plus 2, 10. I end up with my velocity being equal to 15.9 meters per second. 15.9 meters per second. I can go ahead and plug that in. Negative 15.9 meters per second. And then lastly, I can go ahead and use my trig, my Pythagorean theorem, to find velocity. I can do Vx squared plus Vy squared equals velocity squared to find this value right there. And I'm going to go ahead and do that right now.